some student. In case there's some student cannot join this class, they can check the video. So as I mentioned, let's talk about the course project. So let me show you what it has been done in the last year's class. And so you will have some sense what could it look like. Can you see my screen right now?
Yes.
Yep, sounds good. So last year, sorry, the project is a remote control racing car, race car. So that is a full function race car. Actually, I purchased several, I don't remember, 8 or something set of a race car. And I give each of the group one. And basically they can take these parts, components, especially those remote control components and motors from the race car. But for the whole appearance as well as the some of the mechanism, they need to design by themselves and print it by themselves. So that's the original requirement. Of course, they have to, I mean, the result of the project will be checked or marked based on the uniqueness of appearance, the functionalities, and also I would like to see which one runs the fast, right? I mean, runs the fastest. But that was the original source. Actually, we didn't have the chance to physical prototypes due to the COVID pandemic. So it turns out you can see these lines are crossed because, I mean, also because this is not available anymore. So in that sense, we actually didn't have the full goal achieved in last year's course project. Turns out they just submit their design and also the written report, as well as the presentation, 8 minutes presentation, something like this. But for this year, we have the in-person lab session. That's why I'm thinking of still have your design prototyped physically. But on the other hand, sorry, for the previous for this lab session for this project, it's a group project. In each group there are like 4 or 5 people, so everyone will take sorry, a portion of the responsibility for the project. In that sense, if I assign this to you, it will be very heavy loaded because right now there's no group activity. You are working by your own. It's individual. So I would like to simplify this a little bit. So, and also I would like to hear from you. Basically, what it has for last year's project is a car. So I'm thinking of instead of building a car, designing and building a car, I'm thinking of letting you to design a ball pen. Of course, it's a fully functioning ball pen. It has a mechanism to control the tip of the pen. It should does its job, right? You could use it for writing. So the essential parts will be first the appearance. You are required to make the the appearance as unique as possible, right? That's a one requirement. Another thing is, again, the functionality. It should does the job of a ball pen. And the second and third, on the some of the mechanisms, like the springs, you want to print it instead of using existing ones. So think of what could be the processes you will be using to print that spring. Also, you are required to print some of these elastomatic parts. That is using the Formlab printer, which will produce some part with little elasticity. Or you could use the Prusa machine with the flexible filaments. But overall, it's much simpler because you can tell how much it got reduced in terms of the part numbers and also the mechanisms. On the other hand, it still requires efforts and understanding of the manufacturing, 3D printing processes, because you need to select which part to be printed using which. I will specifically ask you to use different processes. Basically, it's similar to what I put here. See, that is what you need. In general, that's the three printers which are available for you: Formlabs, Markforged Onyx, Prusa MK3. I don't think these strategies will be available at this moment. Last year it might be, but in this year it's really difficult to accommodate you with this printer. So instead, think of a design could be produced using Formlab, Form2, Markforged Onyx, and Prusa MK3s. Also, at least one soft electrometric parts, right? Something like this. And functionalities. I cross here because this is for the RC race car, but for the ball pen, it should open it and close it, right? To push it through and get it back, and also the duration of the springs, right? I will try to break it somehow. See, sorry. So whether the spring will be good enough, flexible as well as some rigidity. These are some of the criteria. Also for the deliverables, for the handings, the CAD model, all the files for the 3D printer, they are different. You should understand it, right? So the CAD model means it's 3D design using CAD, but for 3D printing, that refers to the file to be imported to the 3D printer, right? Also, you want to have a written report. Basically, I will pretty much keep these requirements still there. Basically, that's a little intro of your project, and list out the processes, material, and justify why you make the decision for the processes and the materials. Also, some other considerations like strength, cost, speed, color, aesthetics, and some other consideration, whatever you have to affect your decision, you want to list it. So also explain some of the design guidelines for some of the mechanisms, right? You have moving parts, then you want to talk about the minimum feature size and clearance, something like this, to make sure it will first be assembled together, and second, it will still allow the relative motion, right? For the fourth points, I will remove this because it's not a it's not a group project. I hope it's still a group project, a team project, but it's not available for this year's. So this will not be required for this year's project. But more importantly, I will distribute the points, probably 5 to the written report and another 5 to the presentation. So basically you want to record 6-second slides for the introduction and another presentation, 15 or probably 8 minutes to 15. I think 15 is too much. Probably I will reduce it to 8 or 10 minutes oral presentation. Basically, that's how you introduce, how you describe your project. So that's pretty much what I think of how it looked like for this semester's course project. So any questions and concerns from you guys? So I want to listen to you and make adjustment. That's why I didn't post it directly. Instead, I'm kind of want to discuss with you about the details and address them in the finalized project specification. Anything you want to talk with me?
Yes,
Yeah.
Professor. So Jacob and I were thinking that maybe the project can be like the groups that I are that they are already in the lab sessions.
Yeah.
Do you think that could be a possibility? Because they were working. I mean, obviously, each of them are in the in one workstation.
Yeah.
But they could do it the same way, but each of them can take off one part of the project. It could be a group.
So you are saying it is still possible to have a group project instead of an individual one.
Yeah, I mean, maybe they can say what they think, but Jacob and I were discussed that one, and that possibility can
okay.
I don't know.
Okay. So how about I do a poll, see what's the preference from the student. Yeah, let me maybe go ahead and just give you a poll regarding this. Oh, it's not here. Question. Individual or group project. Answer 1's individual. And answer 2 is group.
Yes, but the group should be the same like the lab session.
Okay, group with same as the lab session, right?
Yeah.
Okay.
That will be the easiest way.
Yeah, I mean, it really costs difficulty for the. Oh, where is it? Poll 2. Yeah.
Because one can work in the Prusa, the other one in the Markforged.
Yeah. Oh, that sounds. Oh, the all okay. Just go ahead and make your selection.
Hello.
Yeah, Ariel.
I have a question. So, will the lab sessions be dedicated to group time, like later in the semester, or no?
I mean, actually, you could access the labs anytime, as long as there's a schedule. Because it's complicated. Because for previous course project, it's like you can basically you just go ahead and see whether the printers are available or not, and if yes, you can just go ahead and print. but now there's a little constraints for the access to the labs, right? So in that sense, probably they'll require some scheduling, meaning who will use the lab for what's the time, something like this. But I think in general, it shouldn't be a restriction for the project, only be at the lab time. Yeah. Because you will, I mean, the lab will end before the end of the semester. That means you will have, after that, you will have no labs. So there's no point to still restrict your time to access the lab, right? So that's my answer. So I think it's pretty close. There are 10 select group and 7 select individual. Well, in that sense, still, I think we can go a group. Maybe it's feasible. Then in that sense, I think we can still go with a group project. And also you can then you could naturally form the groups by the current lab sessions, right? So if you are attending the same lab session, you can form the same group. In that sense, you could have a better, I would say, it's easier for us to schedule and also form the groups, because other than that, it's hard to communicate across the group if it's they are, I mean, you are not in the same session. So okay, let's stick to the group still. And for the project, I think we could still go with the ball pen, but I will increase the number of I will increase the requirements by raising up some of the criteria for the for your design and prototyping, such that you will have more work to do, but at the same time you have more people in your team, so that will justify it will justify the requirement for the project. So any other questions or concerns still? No? Okay, good. So another good news is I got back from the Autodesk. They agreed to provide the online courses for the Fusion 360 for the student to access. I just got the administration account set up, and I will invite you to those courses. You should be able to receive an email in the afternoon, and you should be able to access those courses on Coursera. I don't know how to pronounce it, but that's what I get from the Autodesk. If you have any problems to access those courses, just let me know. I will help you to set it up. All right. Any questions? No? Okay, let's move on the lectures. Oh, another thing, sorry. We will be having the first exam. Let me check the schedule. Let's have it on 22nd, March 22nd. Let's have the first exam on March 22nd. So the first exam will cover everything before the photo polymerization. that's basically, it covers what you did for the 2 assignments, the first one and the one you haven't submit. The deadline is tomorrow, right? So basically, you want to check all the content before the photo polymerization. All right, that's the arrangement for exam 2. I mean exam 1. So any question about the exam?
Will we have to be present in the Zoom during the exam, or is it just like a
I think it's difficult for you to essentially for me to really make sure, instead of asking you stay on the Zoom, I would prefer to give you a specific period, like still same as the lecture time, 10 to 12:15, something like this. And I will post the questions at 10:10. Then you complete the exams within this period of time. I submit it to my courses, and that's pretty much what I want to do. Other than that, it's difficult to accommodate the exams.
Okay, thank you.
Yep. Mm-hmm. Okay, let's go back to the lectures. So last time we talked about some of these photopolymerization processes, right? Just 1 second. Are you able to see my screen right now?
Yep.
Okay, good. So we talked about the 2 different stereolithographies, essentially, which are the sorry, the inverted versus the original 3D systems processes, and we compare the pros and the cons between the 2, right? For the inverted stereolithography, which is the one used on the Formlab machines, it has a very low cost laser light source, and the orientation is for the laser projection is from the bottom up to the up, right? And it has a smaller size compared to the original 3D system stereolithography machines. So for the usage of resins, because in the inverted stereolithography, you don't have to fill the whole tank to the full amount. Instead, you just need to fill the resin in the tank based on how much you need to build the part. That actually saves the resin. Also, it reduces the post-processing time if you want to clean the resin after the printing, right? So that's a big benefit. Also, the the price compared to the original 3D systems machine, it's much cheaper. It's quite affordable for us. So we then talk about the vector scan, right? So I discussed this a little bit about the part building times. If we have a given laser scan time VS, this is a linear time for the laser scan, and also the trace width. The width of the trace is WT millimeter. Also, there's a layer thickness, LT millimeter. The total volumes for the part is something like this. Also, you have a overall height for the part, that is h. So as I mentioned, there is some separation operation happening between each of the layer, and at that time you could think of it's a constant time ts, but it happens for each of the layer, after each of the layer actually. So with all this information, how can you compute the total build time? So actually, I give you a little description about it, but let me show you how you can compute it. Just 1 second, I will share another document. I think I will post this document as well. Let me share it again. I don't know if I share it successfully or not. Can you see the solution here? Can you see the slides with a little solution here? So basically,
Yeah, we can see them.
Okay,
Yes.
good. Okay, good. Yeah. So basically, as I mentioned again, you want to figure out the time for the two operators. One is the laser scanning. Another one is the separation, right? So for the laser scanning, you have the total volumes. And then you need to find the volumetric rate, building rate. What you have is the linear scanning rate, the width of the trace, and also the layer thickness. So if you multiply the three together, what you essentially have will be the volumetric scanning rate. Sorry. And you have the overall volumes. Then the time will be this overall volumes over this volume scan rate. And it turns out that will be the total time for the laser scanning, right? That's only one portion of the overall build time. Another one is a separation. So as I mentioned, the separation is a constant for each of the, after each of the layer, it happens. And then what you want to know is how many layers in total you have, right? So basically you have the total height, h, and also a layer thickness, lt. Then you can immediately come up with the number of layers, which is h over lt. So that's the total number of the layers. And use the total number of layers and times the one separation time. Then that gives you the overall separation time, which is essentially this equation. Having the both figuring out, then you can add them together. That will be roughly the overall build time for a part. So any questions for this solving? Okay, I think it's straightforward. A little tricky part is to figure out this volumetric scanning rate. If you, I mean, once this being figured out, there's no problems at all. So we will go back to this file again for another questions, but let's resume to the lecture at this moment. Also, we introduced the InventionTech technology. So instead of laser scanning, I mean, for both the Formlab and also the 3D Systems machine, they are still laser scanning based. I mean, although they are building the parts in different orientation, right? One is from top down, another one is bottom up, but still it's the light source is scanning in lines. It's laser scanning. But for the invention tag, it's different. They don't have a laser beam lines. Instead, they project the 2D images from the bottom to the up. It's a bottom up process, but instead of a laser scanning, they have a projection of the 2D image. In that sense, a benefit for this process is faster, much faster, because it cure one layer simultaneously when one image is projected to the bottom of the horizon, and that's the biggest benefit for this one. That reduces the build time substantially. Another, I would say, a similar process is the SLA. Is another variation of the stereolithography by using the transfer film. So instead of have a tank, it has a transferring film on the platform, and each time a thin layer of resin will be spread on this plastic film, and then the part will be moved onto the newly spread liquid layer, and a light will be projected from bottom to the up. And it turns out the newly spread layer will be solidified and attached to the part. And then the part will move away, and another round of spreading of material will happen on the field. And this will be repeated again and again. I think I showed you the video last lecture, so we will skip the video. But as you can see, it's a little troublesome, right? You have to always move the part back and forth and spread the material. I mean, to me, it's a little time consuming. And also it's critical for the motion of the part. If you move it, if there is a control error for the motion of the moving parts, that could make the build part has geometric error, has problems. So in that sense, that's not to me, it seems not a good solution. So actually, in recent years, there's a new process called continuous liquid interfacing production. In short, it's CLIP. It becomes really vital in the 3D printing world. Also, the founder of, the inventor of this process, which is also the founder of Carbon 3D, were invited to TED. There was a TED presentation by the founder to introduce this process. So what it essentially achieves is a continuous lifting. So even for the invention tag printer, there's still a separation motion. It happens for the Formlabs, it happens for the invention tag machines. What happens, it happens for this transfer film process. So what it does is because the layer is at the bottom of the platform or the tank, so there will be a risk that is the newly generated layer get sticky to the bottom. So to solve these problems, once a layer is built, there will be a linear motion of the platform or the part to separate the part from the bottom of the platform or the tank. So that actually cost substantial time. So basically this clip process skips this separation process, and which essentially improves the efficiency of the process. Let's look at. So as you might notice, it has a key technology, which is the oxygen layers, which they call the dead zone or dead zone in their process. So what it does is they have let me have a pen here. They have the oxygen layer put here to prevent the liquid resin got cured in this region. So it turns out there's no resin curing happens within this region. So in that sense, there's no actually attachment of the part and the bottom of the tank. So in that sense, it prevents this linear motion. It skips. There's no use to do this separation motion. That's why they could continuously lift the parts without this linear motion to separate the parts from the bottom of the tank. And also here you can see those liquid goes a flow. I mean, these liquid flows go to these directions to fill the space because of the lifting and the curing of the parts. So that's how that's the dynamic process. It happens when a part is printed. Any questions so far about this process? Okay, so you understand it, right? So that's I mean, in principle, it's very simple, but it's not an easy task to realize it. Actually, the team is from Duke University, and essentially they are from chemistry department, and it takes substantial effort to come up with this solution, sorry, that's how they could build up a company based on this idea. I mean, that's not an easy job to do. They publish paper as well on science, and at the same time they file the patent to start up their company. But there is also a problems, fundamental limitations for this process. Can you think of any direction which could be the limitation? No. Yeah, I mean, the major limitation for this process is still it cannot be used to build a large size part. Why? Because of this liquid flow, right? Although there's no attachment of the part with the bottom tank in this region, but still it takes time for those flow to fill this region. Just imagine if you have a really large size for here, and once it is lifted, cured and lifted, it will take a significant amount of time for the flow to fill this region, and that is not undesired. That is not desired, because you have to wait until this is fully filled, and then you can only start the curing. So in that sense, if you are building a too large, building a part with large cross section with large areas, that would require a synchronization time. That is, you have to wait until the flow, the liquid flow, fill in the regions. So that will slow down the process, and it will. If the part is larger, this time for the liquid flow to fill in will also become larger, and that essentially slow down this process. So that's why what you see in the video is something only have a thin shell, right? The region, the actually part cross section region is small, or some thin frame structures. That means there's only small regions to be built instead of a large contact area of the part and also the bottom of the tank. So that's the fundamental limitation for this process, and it hasn't been solved yet. So yeah, but they won't tell you in their videos, right? So any other questions? Okay, good. As I mentioned, you can see in all their demonstrations, they have such kind of parts, right? That means it's not a bulky, solid part with a large cross-section regions. Instead, it has a small, I would say cross-section regions, and it will not fill this liquid fill in. So, but anyway, let's do a little comparison between the Formlabs and the Clips. We have compared Formlabs with the 3D system process. Let's do a little comparison between the Formlabs and the Clip. So as I mentioned, for the Formlabs, there is the adhesion force for the parts and also the bottom of the tank. So there must be a separation operation. But for the Clip, because of the oxygen permeable window, the so-called dead zone prevent the actual touch of the part as well with the bottom of the tank. So that will avoid this separation and enable a continuous lifting. But on the other hand, I mean, therefore, the building speed is faster, right? Compared much faster than the Formlab process. But still, it's limited to print small parts because of this liquid flowing issues, right?
I got a question, Professor.
Yeah, go ahead.
For the clip, do you need like an external oxygen tank, or does it just like bubble in from the atmosphere?
It is integrated. I mean, for the prototyping system, I saw it. Actually, I had a friend working at University of Buffalo. He came up very a similar idea at the roughly same time when Clip launched their product. What his setup is, yes, there is a oxygen tank, I mean bottle there to continuously provides oxygen there. But I mean, but he didn't apply the patent, and that's why Carbon started up a company, but he didn't. But anyway, for their machine, they have such a built-in functions there. So essentially, there's no need. Yeah.
Thank you.
Yeah. Of course, there could be some supplies you need to purchase from them, but that's it. Yeah, you don't have to worry about that yourself. So that's another video. I mean, very famous one for the Carbon to demonstrate their processes. But for this process, because you don't have a separation operation, that means you don't have the time associated with it. The only thing is the layers. How many layers you have, and how much time it costs for building one layer, right? So just simply multiply the two together, you will have the total build time. That is the layer build time and also how many layers, and multiply the two, you will have the overall build time. There's no such a separation time in between of the two layers. So that's a different for this clip process when you compute the time versus the Formlab printers. All right, or the InventionTAC printers. So as you can see, from the 3D system printer to Formlab to InventionTAC to Clip, roughly it's an evolution, right? The 3D system machine is the original stereolithography. It's a laser scan. It's from top down, right? From the top to the downside when you build it. Then we have the Formlab that is from bottom up, but still the laser scanning process. Then people think, okay, how could we further reduce the time? That is, keep the bottom up building direction, but replacing the laser to be a projection image. That further save the time. But still, it requires a separation for the Formlabs and also the InventionTAC one. And then people are thinking, okay, how we could even avoid this separation? That's how the clip gets its attention and reduce the separation process, essentially. But still, there's a limitation. That is the flow of the liquid. That is too slow. So again, it suggests the research direction and the people's efforts, where people's efforts should go to. So hopefully there could be some new process which solve this problems even. And in that sense, that will make this stereolithography process even better. And that could be a good thing for the consumer as well. All right. So that's pretty much the fundamental of stereolithography. And then we will talk about some of the variations of these processes. But let's have a break now and come back at 11:10. All right. let's go back to the lecture. So let me share the screen. So other than directly build the part using stereolithography, there are also the processes which will be used to do the composite 3D printing. So that is basically some of the material like ceramic are filled, are combined with the polymers, photo curing polymers. And then this combined material, this mixed material will be used for the normal stereolithography. And after the part is completed, obviously it's not a final part. It's more like the grain part in the casting. That is, it has a geometry, but the mechanical property, the stiffness of the part is not good. So that requires two other steps. One is the debinding, that is to remove the binder. More intuitively, like glues or the polymers. Basically you just heat it up, and then the polymers or the glues will be burned out. Then there will be the centering part, that is solidify those ceramic particles. Basically you want to really heat it up to a high temperature. Here shows us a strategy to center the part. There are different times with different temperatures. After this centering, basically you want to cool down the part naturally. And turns out you will have a final completed part built. So the benefit for this process is, well, it can build really complex geometry, which cannot be produced using other processes. Also, it's a cheaper process than those machining process, for example. So there will be a shrinkage. I mean, similar as other casting process, there will be a shrinkage during the debinding and also the centering, because the volumes of the binder will be excluded, as well as there will be particle fusion during the centering. So it again will reduce the volumes of the parts. So how to control this shrinkage will be essential, because you want to know what will be the final part you will have, even at the stage of design, such that you will know how to design your part, how to compensate the shrinkage of the part. But that's a variation of stereolithography based on the stereolithography. Another process detail is this laser galvanometer. For the laser scanning based method, as I mentioned, basically the laser beam is directed to scan a pattern on the build platform. So how to achieve this direction change for the laser beam? So actually it is achieved by these galvanometers. So for a galvanometer, there are two mirrors, as you can see in this image. There are 2 meters. One will be rotated along the x-axis. Another one rotate along the y-axis. So by combine the two rotation, you should be able to direct the laser beam to scan any point on a 2D plane, which is essentially for one layer, right? And let's look at a video about this galvanometer. I think there's no captions. Basically, this video describes how it works, and there's no captions. I'm sorry about that. But basically, there are two motors to control the rotation of the two mirrors, such that will change the direction of the laser beam. So you can understand it. Also, maybe this one has a caption. Let me try. Yeah, it has the narratives on it. Basically, it shows again how the galvanometer work. See, there are two galvanometers. See, the laser beam is guided to scan in a pattern, and that's how it works. It's similar to other, I mean, this is not for 3D printer, it's more like a to make holes, right? But same thing happens in the 3D printer. Basically, you want to use those mirrors to change the direction of laser beams to scan a pattern, and that's it. That's how it works. Another very important components in these laser-based process is the f-theta lenses. So if we look at the conventional spherical lenses, what it does is it will focus a parallel light to some spot, right? But the problem is all the focused point, actually they are on a curved surface. It's a spherical surface. In that sense, if let's say this is the build platform, which is a plane. And if you just use the spherical lens to guide the direction of the laser beams, it turns out all the focus are on this. Sorry, I need to. Yeah. All the focus are on this spherical surface instead of on the plane. So when it travels to the plane, it is not focused, it's defocused. So then you have no control on the accuracy of these light anymore. So instead of a small spot, it will have a larger area covered on the platform. And that will make the feature size and details of the 3D printed layer, I mean the layers, not what you want. So in that sense, it really need to have a process that is make sure the focus is on this 2D plane instead of this spherical surface. So actually that is what this f-theta lenses does. So there are a family of lenses, a combination of them to make sure this after passing through the lens, this light will still have the focus on the 2D plane instead of on this curved surface. In that sense, it will solve the defocusing problems in this projection. So any question about this f-theta lenses? No? Okay, good. Yeah, so I don't want to go to details about these lenses, but just give you the basic concept of how it works and what it does. So the final thing is the digital light projection. So basically you will have it in your projector. In every modern projector, it has such kind of a family of mirrors. So these macro mirror arrays, they are available for visible light, ultraviolet light, or near infrared light. And it has for each of the macro layer, mirror, there's a control beneath it. So it will, these control are separated. So in that sense, it will tilt the mirror separately in certain angle, such that the projected light will be different. So it have a very flexible control on the projected light, and such that it could be utilized for the projection-based stereolithography process. For example, the InventionTEC machines as well as the CLIP, right? They are projection-based. So then there will be a question, because you are projecting an image to the build platform. So that will be a question about the image size and also the build resolution. So how you find out the relationship between the two? There's one thing you want to keep in mind, that is the image projected by the projector. It has a fixed pixel numbers or some different options. You could choose 1920 by 1080. That means it has a width with 1920 pixels and has a length that is 1080 pixels. So it has that much pixels for the projected image. For other projector, it has other available resolutions, and that is associated with the macro mirror array size. So each of the macro mirror array will be corresponding to 1 pixel, and that is determined by its physical components, right? So in that sense, with the pixel number fixed, how you decide the projection image? If we look at this illustration figure, right? Here, that's the where the projector is, and basically it projects a image onto this build platform, and with a certain distance, right? Then you can tell what is the size of the projected image. It has a width this much and the length this much. And remember, on such kind of rectangular area, actually the image with the fixed amount of pixel is projected. So that means there will be pixels like this listed, just some illustration along this one and this one, this one, this one, right? Then you can tell what is the size for the edge of each of the pixel. If you look at the pixel, each of the pixel, you want to know what is the size of the length and width of this pixel, right? You want to compute this. Let me use X prime and Y prime to represent. You want to compute these, and that tells you the minima 3D printing 3D printed feature size, because that is how you represent an image and how you cure the region in this platform, on this platform. So essentially you want to compute the pixel size, you want to compute the projected pixel size on this platform. So how you want to do is you have this length, you have this depth information, and you have the angle of the projection. Also, you have the resolution, the pixel numbers of the image, and then you should be able to tell it, right? Actually, I can show you how you compute in just with this example. All right. Let me open another slide. So same slides on the as the one on the lecture notes. Let's see, this projector is able to project an image with this much resolution, which is 1920 by 1080. Also, this distance is not question mark again. It's a known number, 40 millimeters. Then what is the smallest size of the printer can be printed in X and the Y direction? As I mentioned, essentially you want to compute for each of the pixel to be projected onto this plane, what is the length and width of the projected pixel, right? So first thing first, let's compute what will be the size of the image projected onto this this plane. Because you have the angle here, right? And you have this distance. Use some trigonometry if you separate this triangle to 2. So for this angle, that will be 13, right? 13 degrees. And this height is same as the height given, 40, right? And this is 90 degrees. So the height is perpendicular to the plane, right? Knowing this, basically you want to compute this, right? And that is, you can use the tangent. That is tangent 13 times 40. So that will be this length. And it turns out you can come up with the number that is 18.5. But that's for the x-axis. So in the y-axis, it has a different angle. That is 19 degrees. So this is for the x and this is for the y, right? Do the same thing for the y as well. Basically, separate to 2. This is perpendicular, and this is the 9 degrees, and 40 again. And then you come up with this in the y direction. So it turns out the number is 12.7. In that sense, the original image, the image with this 1920 by 1080 resolution, it is projected to the plane, which is 40 millimeter away, and it will has a size of the projected image 18.5 millimeter times 12.7 millimeter. As I mentioned, for this much, for this amount of this large projected image, it has a similar image resolution. That is not similar. It's exact same image resolution. That is 1920 and 1080. Then over this, accordingly, you will have the pixel size, projected pixel size on that plane in the x direction, which is this number, and in the y direction, that is this number, right? So any question?
I have a question.
Yeah.
For the x direction, I get where you got the tangent of 13 degrees times 40, but where is that extra 2 coming from?
Oh, okay. Yeah, that's a good question. I forgot to mention it, but you are computing this half, but what you want is the whole,
Okay.
right? Same thing
Yeah.
happens here. So that's why you always want to have 2 multiplied of onto this, right? That's how you come up with the dimension of a projected image in the x and in the y axis.
Okay. Thank you.
Mm-hmm. So by looking at this, you will have an intuitive understanding. That is, if you have a farther distance from the projector to the plane, the image will be larger and larger. But the thing is, still the image has the same resolution. That means the smallest feature will be larger and larger. That is what you could do smallest will be larger and larger. That essentially reduce the quality of the printing. So in that sense, you really want to restrict the projector the distance between the projector and the projection plane to make it not too big. Otherwise, the printing quality will drop significantly. And in that sense, it cannot print really large part, because if you want to print a large area, you have to move the projector farther from the printing platform, and essentially make the resolution of smallest feature larger. So there is a balance. You can tell there's a balance between the smallest feature versus the size to be printed. There's no way to have them all. You have to balance them. All right. Okay, that's for the digital light processing resolution and image size computation. So that will be some homework, some questions associated with this. So be aware to this. Of course, I will share these slides with with you. You can find it on my courses, but be sure to understand how you come up with these numbers. All right. Any other questions? No? Okay, good. Let me stop the sharing. So another thing you want to think of is the laser or light wavelengths. There are different wavelengths for different light sources. For ultraviolet, violet, and blue light, it have different wavelengths, and this will affect whether you could cure certain polymer, liquid polymer or not. And definitely you want to select them carefully when you before you decide to use certain material, whether this machine is capable to cure it or not, something like this. Here shows you some of these numbers here, and you could take it as a references. Also, the material properties associated with the light sources, right? Some of the discussions. Basically, there are problems for the building accuracies that is during the processes, there will be the curving, right? That is, I mean, there will be some shrinkage, as I mentioned, because when the liquid becomes the solid during this phase transition process, the size of the material will become smaller, and essentially that causes shrinkage, and that will be the major problems for the accuracy, and that's the fundamental limitation for this. Sorry. Also, there are sometimes the not always the stiffness are the main concerns for the processes. For some of the applications which requires the relative motion, the flexibility may be more important. Then you want to think of other material property as well. For example, the living hinges. There's always relative motion, rotational or the linear motion associated with it. So definitely you want to have the higher flexibility other than the higher stiffness. Also, there are some applications that require higher temperatures, higher temperature resistance. For example, for some part that like used in the car part, and there will be a substantial amount of heat during the car is in use. And in that case, you have to make sure the material you choose will have a high temperature resistance in order to fulfill the requirement. Also, there are some applications. I don't know whether you were aware of some of the 3D printed lenses for glasses. Basically, they use the stereolithography based process to print the lenses. Because for everybody, although there are some standard numbers for your glasses, but it's preferable to have a full customized lens. In that sense, 3D printing can help. Stereolithography can help. And for such kind of applications, you want to have a really good optical clarity. Another example is the invisible teeth alignment, right? So the selling point for such kind of teeth alignment aligner is it's invisible, means you cannot, I mean, it's not that noticeable or you cannot see it. So in that kind of applications, definitely the optical clarity is a very important feature you want to achieve. And yeah, these are some interesting point for the stereolithography's material. Okay, I think that's pretty much about the fundamental processes of stereolithography. And we can, let me, sorry, let me go to the other slides about the some science, material science about associated with stereolithography. So first of all is the polymers. That is the material utilized in the stereolithography. So for the stereolithography, there will be a phenomenon called cross-linking. So basically, the cross-links will link the different the different chains of polymers into one by one. And you can see here shows the difference before a non-cross-linked and cross-linked polymers. So that will really change the material property of the oh, sorry, of the parts. So, but that's what the polymer material property unique compared to the thermoplastic. In the thermoplastic, there's no cross links, right? In thermoplastic, it's like spaghettis, right? Noodles, or they are not connected. So in that sense, the polymers, photopolymers, cannot be reproduced different from the thermoplastics. So it will not be allowed to reuse once they have been cured. It has a good covalent bonds compared to the thermoplastic. Also, the glass transition temperature got increased significantly because of this cross-linking. Also, it has a very good resistance to the solvents. The temperature, the bearing, I mean the sorry, the temperature photopolymer could bear with is in general much higher than the ones bared by thermoplastics. So, which is good properties. And this again is associated with the applications. When you have some applications with some aspects associated with the temperature resistance, whether it will be resistant to a solvent, so on and so forth. You want to compare the thermoplastic and also photopolymers and make your decision. You may ask, because I mean, thermoplastic looks worse than the photopolymer, why you still consider about it? That is compared to the photopolymer is much simpler to print using the thermoplastic. Also, it's much cheaper. So these are the two advantages for the thermoplastic. You cannot actually afford it if you you cannot justify you need such kind of properties when using the photopolymers. So that's why you want to compare them when have a specific application and make decisions, right, based on it. Then we talk about the photo curing. So this photo curing is I would say a very tricky part in this photopolymerization, and there are several concepts listed here. One is the penetration depths. So this penetration depths describes the depths beneath the liquid surface at which the energy intensity has been reduced to approximately 1/3 of the intensity at the surface. Actually, if make it more precise, instead of putting approximately 1/3, you could put approximately 1/E, where E is the Euler numbers. So that is if the energy intensity decreases to sorry, to 1/E of the intensity at the surface, that depth will be the penetration depth. So this penetration depth is associated with the material property of the photopolymer. Another concept is the scanning velocity, especially in the laser beam-based processes. So it describes the speed, linear speed at which the laser beam is scanning over the liquid resin. Another concept is so-called the critical exposure. That is the energy intensity per, basically you can take it as energy per unit or energy per unit area or energy intensity, surface energy intensity. 10 CT. Okay, they are equivalent in this case. The energy intensity needed to produce gelation of the photopolymer. So basically, if the energy intensity you provide is not beyond this EC, you will have not the liquid material to be cured. So that's why this is called critical exposure, right? Literally, it's critical. And the cure depths, basically that is a function of all these threes. The penetration depths, critical exposure, energy intensity, exposure area, and exposure time. So this is the cure depths is determined by all these and some other aspects. So it looks like, it looks very complex, and it is complex. So actually the laser exposure or energy intensity for the laser in the resin is something like this. If you look at this figure, I think if we take this figure, that will easier to understand. So basically, this is the cross-section view of a trace. Basically, you could think of, okay, you have a trace, and it has such cross sections. Oh, I think this one looks bad. Let me clean this up. Something like this. So the cross section is this bell shape, like this, and it will go along with the same direction of the laser scans, right? Just have the idea of what it looked like, right? And basically, this area is the cross section area, and now you get it, right? It's, for this region. And then you have a laser, and this laser exposure is a function, is like Gaussian function. You can see when you talk about the laser exposure on the z-axis, that is y equal to 0, it has the maximum laser intensity, maximum laser exposure. And it will decrease if it go away from this center. It will decrease further and further until at this point it becomes 0. There's no energy intensity anymore. And of course, the region go beyond will not be cured. But as you can see, even there are some energy intensity still in this region. The liquid is not, the liquid resin in this region is not cured because it not go beyond the critical, critical exposure. So that's why we have this critical exposure. That means, well, even you have some energy, but it does not go beyond the critical exposure. Still, the material will not be cured. So that's why this length is different from the span of the laser. That is because the critical exposure. So how do you feel so far? Understand or confused? Any idea? Okay, good. So let's take detailed look at it. Again, let's look at these numbers. These notations. So sorry. So this PL is the laser power, right? And W0 is the Gaussian half width of the beam. That is the so-called as well as the beam radius. So essentially it gives you this. Oh, I think I need to clean this up. So it gives you this. That is the W0, which is the Gaussian half width of the beam. So if you talk about the beam diameter, that will be 2 times W0. That will be this full length. All right, so you need to keep this in mind. Sometimes the question will give you the beam diameter instead of beam radius. So be aware of this. And also, there's a velocity of the beam. That is how fast the laser beam scans. And the penetration depth, which is the depth at which energy is 1/E, that of the energy at the surfaces. And so that's the penetration depth. And by putting these together to this equation, there's an exponential function, right? And you have this laser exposure in the resin, and Y and Z gives you the idea at where you want to measure the laser exposure. So you will find one point in these regions or these regions, and at each point, when you substitute to this function, it will return you a energy exposure by giving a specific Y and Z value, and essentially that's the position in these regions. So any questions so far? Okay, still fine, right? So I just keep it slow because it's a really complicated equation, and I just want to make sure what I said will be fully understood by you. So let's look at some of the more explanations. So what are the parameters in this function that is determined by the laser or the laser scanning speed, laser scanning system? So first thing first, that is the power, right? You can control the power for the laser scanning. Another thing is this laser scanning speed. So PL and VS are the function of the laser or the laser scanning system. That is what you could control by tune the laser. Then what are the parameters which are functions of the resin you choose? As I mentioned, the penetration depth is associated with the material, with the resin itself. So this dP here is the penetration depth. It represents what is the depth at which the energy intensity reduced to 1/E of that on the surface. So in that sense, dP is associated with the material property of the resin. So now we have a little understanding of this equation. Then the question would be, okay, if we increase the scanning speed, what happened to this term? Increase this VS, at the same time keep all other parameters the same, and use the same resin. So what will this PL over W0 times VS change? Any question? I mean, any idea?
It'll decrease.
Decrease, right? And just to think about it. If basically you want to use the laser to cure the resin, what you want to do is you want to make sure the laser will stay enough time in order to cure the material, but it will, if it scans really fast, choo, that means probably it's too fast to cure the material, and that will decrease the energy intensity in that sense. So essentially this E function will be decreased if you have a too fast scanning velocity. And that makes intuitive sense, right? Just to push it to the extreme case. If it's too fast and nothing happens, right? Something like this. If we look at a very simple calculation, so what is the laser exposure at depths of 0.05 millimeter and a lateral distance of 0.03 millimeter from the center of the beam? So it turns out gives you the, what is the Z here? That's here, right? That's the Z. And what is Y? And that is here. So use these two, and also you have the laser power, what is this again? I don't remember. Gaussian half width, the laser readers, yeah, laser readers. Laser readers and scanning speed, and also penetration depth. Then substitute everything to the equation, right? To this equation, and turns out it will give you this number. But that's the, I mean, simplest question associated with this equation, because it's straightforward, right? You just substitute what are given, and you will have the laser exposure computed. But sometimes it could be critical to have some understanding about the sorry, some concept like the critical exposure. As I mentioned, sorry, the critical exposure will be needed to initiate the curing. That is, if the energy intensity or the laser exposure is below this EC, that is, nothing happens, no curing happens. That is very important, the critical exposure. You have to go beyond this EC such that there will be curing happens. And if you look at the figure, you will realize actually the width of the curing line at the surface will be associated with the critical exposure, right? Another concept is the scan pitch. If you look at, again, these are the cross sections of the trees. If you see, if you look at it, basically this is one tree, and this another, and another one, and another one, and there are some gaps between those different trees. That will cause problems for those void, and low stiff regions, low stiffness regions for the build part, so which are not desired. That means you want to control these scan pitches to make sure there are enough overlaps such that those empty regions will be minimized. So that's the sorry, that's scan pitches. Another one is the layer pitches. That is, what is the distance between a new layer and a previous layer? So you could make more overlap in this direction as well, or decrease them. And that again will change the material property of the built part. And these are the ones you want to also think of when when you look at the the processes of stereolithography. So as I mentioned, the cure depth is a function of all the concepts associated with the laser exposure and also other aspects. So it turns out what you will have is the maximum depth, cure depth is something like this. And there are new value here, the Emax, which is the maximum exposure energy. And this Emax can be computed because as I mentioned, you will have the maximum energy, exposure energy only when you are located at this point. That is y equal to 0, x z equal to 0, and then you will have the maximum exposure energy. So substitute these two zeros to this equation, and turns out this part is not there. And turns out this E function gives you 1. Overall, it gives you 1. And then the Emax is this number. And you can substitute this E1 to this, and it turns out you will have the maximum cure depth, right? Sometimes you will have the laser velocity known, and the question could ask you, what is the desired cure depth? With a given laser velocity, what is the desired cure depth? Then you will have such a relationship. Sorry. And what you want to know is this CD star, right? And what you know is the VS. So then you could do the reverse computation. Divide VS by this term and use the ln function to have this, and multiply dp to this side, and turns out you will have the CD star. So that could be one way to ask you. That is, knowing the laser velocity and you want to compute the desired cure depth. But also, if you have a desired cure depth, you want to determine what is the laser velocity. That is, you know CD star, and what is the VS. That would be easier, right? You have the CD star substitute here, and immediately you have the laser velocity computed. So these are all the possible questions for the homeworks and again, the exams. You want to think through by checking this equation and figure out what's the situation when these numbers, when this happens, right? Okay, I think we can look at one example again. So I think it's essential to give you some specific cases, right? Let me share this again. Oh, I think we do not have enough time to explain it. Okay, let's leave it to the next class, but I will post that question and the solution just after the class, this class. So you can check it yourself, and we can have little discussion in the beginning of next class. But that's pretty much all for today's lecture. Thanks for your attention. All right.
Thank you. Take care.
Yeah.
Thank you, Professor. Have a good week.
Thank you.
Yeah, you too. Bye, guys.